success or failure. It takes in just two outcomes, right? So we have this, and then when we say binom.pmf, so why we use PDF for continuous random variable? So we have the binom, which is the binomial, right? .pmf. And remember, we imported it from scipy.stats, and then here we have the x, which is the list of outcomes that we have, that 0, 1, 2, 3 to 10, 0 to 10 now, and then we have the N now, which is the number of trials, and then P, which is the probability of success. So when we print this out, so we are seeing that the probability of getting a zero is the probability of getting zero head, like in this trial that we just did now, probability of getting zero head is 0.00. This is the value. The probability of getting one, probability of getting two, probability of getting three, four, five, like that. So now when we visualize this, so we have the x here now, that's from the 1 0 to 10, and then we have the probability also. So you see here we can visually see this, that the probability of having no heads at all is very low, right? The probability of having one is this, probability of having two, so it keeps increasing, and the highest being five, because we set this to be the probability of head occurring is 0.5. So if we change this now, I think this was relating to a question that Joshua asked last time. So if you change this now, you see that because this is 0.7, so it has, so 7 will be like the highest. So it has a high chance of occurring, right? So we know how visualization works now. So we're using our matplotlib, right? As we imported it as PLT, and we're using the bar, which helps us to create like a histogram, like a bar chart. And then we plot this on the x-axis, and we plot the probability of this occurring on the y-axis. So we're going to play with some examples, and we'll see how some of this works. All right. So now, okay, let's go into some of the examples so that we can appreciate this. So for reproducibility, so that when you run the code, you keep getting the same results I get. So remember, we can set seed. Let me do it in a different. So remember, we can set seed, because the moment we keep using all of this random this thing, because it generates it randomly, and each time you run it, you get a different values, right? So we need to set this so that we can, let's say 28. So we keep having the same results all through whenever we use random. So let's take this example now that we have.
Sorry, sir. Good evening.
Okay, good
How
evening.
did you reach that value, 28?
No, it's just a random variable. I'm just using, like, it's just random,
Okay, sir.
because this now it keeps produce each time you run, each time you use the random dot something, it keeps producing different values. So you have to keep having the same value. You can set, you can make it anything here at all. So let's name it one or two. So it doesn't matter. It just
Okay,
so that if you run it on your system, you get a consistent result with what I'm getting here. Because so let's look at this question now. We have they said a factory produces light bulb with 5% defect rate. So if we sample 20 bulbs, what is the probability of finding exactly two defects? So now what we saw last week was what's the probability that there will be defects, right? So what's the probability of having, so we simulated the whole process, right? That if I to take this sample of these 20 bulbs and keep checking it, right? How many defects are we going to be getting? So over time, we can do that, that you can do that for like maybe 50 or you can do that 100 times, right? So that you can now see the distribution of the number of defects you'll be getting each time you sample 20 bulbs. But now we are looking at it from the from the aspect of, now you are from the statistical aspect. Now you have 20 bulbs. What is the probability that exactly two will be defective? If you look at this, is either it is defective or it is not defective. So it has two possible outcomes. So this is a binomial distribution, right? It follows a binomial distribution because that's two possible outcomes. So that's how you know that, okay, this is a binomial distribution. Now, when I'll tell you how to identify other kinds of distribution also, right? So that you can know, what to use. Now, we know that for the binomial distribution, we use the binom.pmf, right? Not PDF, right? Because this is a discrete random variable. So you cannot get like a 1.5 bulb that is 1.5 bulb that is defective. So it's either it is one bulb that's defective or two bulbs. So you can't get like a decimal number in between. Now, so we use this, and it takes in what? Number one, it takes in the range of values, right? And then we have the number of trials we want to do, and also the probability, right? So when we look at this now, so we see that we have, what can we take from here? So what have they made available for us? So the first thing we see is a factory producing light bulb with 5% defect rate. So already we know that the probability is 5. So we say this is 5% now. That will be 0.05. And then also you said if we sample 20 bulbs, so our n, our sample size is 20. All right. So remember the difference between a sample and a population. So a population is the total number of elements or people or in the should I say in the location of interest now, or the total number you are interested in, the total number of people now you're interested in, right? So that's like the whole population. And then when we look at sample is just a subset of that population, just taking a part of that population. So we call that a subset. And so when we have this now, we have the sample bulb 20, and then said what is the probability of finding exactly two that are defective, right? So let's take a range. So it could be one, it could be two, it could be three. So let's just create a list of numbers to simulate things. So we have NP, that's a range, right? And then we want to find the probability, right? So now here we saw that we did binom.pmf, and then we just did this, right? So remember all of this now. Let me change this to 5 so we can. So we see that this is the probability like 1, 2, and the rest of them like that. And then we see the fifth one, this now being the highest, right? So that's why you will see here would increase that way. So let me run this now so that we can see what I'm talking about. All right. So, but in this case now, we have to specifically find probability of having exactly two. Let's just do it the way we did it the previous example, and then let's see, and then I'll show you how to just get the value. So first of all, what's entering here is our, okay, let's use X for consistency. So we say X here, right? And then the next thing is our N, and then our P, the probability. So we can also print this out so that we see how it looks like. So we just get like some bunch of numbers because this gives us the probability. So you'll be expecting numbers between zeros and ones. So remember, this is e raised by minus one. So that means you're saying you're going to take this back, right? So this is like 0.35. So this like that. So this is just representing in standard form. So to visualize this now, so we call our PLT, right? So we say PLT dot bar, and then we pass in the X and the probability. We want the probability to be on the y-axis. I want the numbers of outcomes to be on the x-axis. So when we do this, we don't need to do all fancy things. We can just simply use PL to just show, but you already know what is your x-axis and y-axis. So when we run this, we see that the number of 2 is between, or the probability of having a 2 now is between 0. So already we can see it from here. You can try to check the value from here, but you can visualize it to know, or you can also use the stats here. Do I have that package installed? I don't think I installed it. So let me import that package. All right, so basically we still get the same thing. And then we can look at the value here for the 2. And then we now note the value of getting the probability of finding the exactly two defective bulbs. So I believe this throws some light to how we can actually use some of this distribution to get results, right? So you could simulate this many times and then see how it behaves. Now, so we're talking about we'll go to the Poisson distribution. And the Poisson distribution now it models the number of events happening in a fixed interval of time. Whenever time is involved, right, is a very good indication that the distribution you're dealing with is a Poisson distribution. So, for example, like the numbers of cars that passes in an hour. So the number of calls you get, the average number of calls you get in a particular time frame. So whenever you see some of all this in the example in the exercise is indicating Poisson distribution. And Poisson distribution has only one parameter, which is lambda, and is the mean. So it's the expected number of events per interval. So here we want to simulate something like that. So we are saying that, for example, this is representing the number of calls a particular company gets, or maybe a particular service provider gets. So we get like, okay, 3 calls in an hour. So we represent that with lambda. Now the reason why we're putting this is because lambda is a keyword. So we want to use underscore here to differentiate it. Then we have x np dot a range, and then we get the numbers of outcomes, possible number of outcomes. So at the end of the day, right, these calls could be zero, it could be one, it could be two, it could be three, it could be four. So now we want to show this distribution and see how the probability works now. So when we say that the average call is three, right? So what is now the probability that in that hour you're going to get maybe 10 calls? So we see that the probability of getting 10 calls now is very low here, 0.002. Probability of having no call at all is even a bit higher than the 10 calls, right? So that the probability of having exactly, because the mean is around three, so there'll be a very high chance that you either get two or three or like four. So this is the highest number will be between two, three, and four. So this case now you can make prediction how many calls with this person be getting in the next 1 hour. So basically this will also depend on maybe the whole when we have the whole data set, right? And we look at the pattern. Maybe there's a particular hour that most people tend to make place calls towards in to that company. We can also use that to we can model that and then predict the number of calls we'll be getting so that you can have sufficient people. Now just like you're going to the bank now, sometimes when you get to the bank you see that some of the cashiers are not around and then there are many people, so you need to know the rush hours so that you can be able to reduce wait time. Because at the end of the day, as a mathematician, as a statistician, as a data scientist, you want to be able to minimize cost and maximize profit. Right? You want to make sure you make use of whatever resources you have because resources are limited. So that's the job. So now when we have time is a resource, right? So these customers, you want to offer the best service to them. So you want to make sure that what is the minimum number of maybe service cashiers that should be around to make sure that the wait time is reduced to the minimum. Of course, you cannot just employ 10 people. You cannot just have 10 cashiers there and then what of times when people are not so common. So most of them will now be idle, right? So these are some of the things we need to look at. So when we have the full data, we can understand this better. So, but now we'll look at an example to see how we can make. So when we represent this now, when we visualize this, we see how it works. So we see that there's a very high chance. In fact, they're almost equal from here 2.2. Oh, they're even the same, right? So that's in an hour you get 2 calls and 3 calls. So you can you know visualize this and see how it works. Now let's take an example. Let's take an example. So we have a cafe. I'm still after this, we're going to still go through another set of examples so that we can apply some of these things. So now we have a cafe receives. Okay, let me get this here so we can. A cafe receives a cafe receives an average of 12 customers per hour. So what is the probability of 15 customers arriving? So of course, I told you when we talk about time is a big indicator that it's a Poisson distribution. Now, and in this case, we can see customers, humans. So we cannot get this is a discrete random variable, right? It's not a continuous because you can't get 11.89 customers. You can't get whole number. So this is a discrete random variable. And when we see that time relating to time, we know that this is a Poisson distribution. So now, how do we, they say, what's the probability of 15 customers? What's the probability of having 15 customers? So they usually get 12 customers in an hour. So what's the probability of having 15 customers arriving in an hour so that you can prepare for that? So now what's the first thing to do? So we have the lambda. So for the cafe, so we can call that lambda cafe, right? So and then we have that to be 12. Also, we need to now remember previously we've been using 0 to 10. So let's define our x now. So for this Poisson distribution, you don't need to put the probability, right? That's the p. It only takes in the lambda and the x. So for the x now, we need to also simulate outcomes, different outcomes. Since we want the probability of having a 15 customers. So now our range should be maybe between 0 to 20 so that it's more than that 15. Let's make it 25 since the average is 15. So it's possible to have up to 25 or even 30, right? Customers in an hour. So but let's just say the probability that in an hour the kind of the different probabilities of having different numbers of customers within an hour. So we call this, let's call it okay, cafe probability, right? And then we use the Poisson. So remember, it's since it's a discrete random variable, it will be PMF. And then we have our X and our lambda. Okay. So, all right. I think that's good. So we have the cafe. So let's run this. And we have this. So now this is the probability of having um, you know, 0 customers within an hour, probability of having 1 customer. So let's visualize this because the numbers are not looking nice. So if you want to visualize it, of course, quickly our p lt dot bar, and then we pass in what x, and then the lambda. Okay. So, so there's something wrong somewhere. Okay, what's happening? All right, this is not supposed to. Let's use k here. They can't have it's clear. Okay. Mhm. Okay. This is, let me see. All right, let me use Seaborn to see the difference that I have with Seaborn here. Okay. All right, so let's all right, let me use Seaborn to see the difference, so to know what's going on. So CNS, then we have bar plots, and then we have our X and our lambda.
So I did not add A after the lambda.
Oh, okay. Thank you.
Then you're also supposed to change to K, I think, right?
Oh, there's a lot of things. Yeah, so we see bar plot X only one argument, you know. So let's say our X is equal to this, and our Y is equal to this. It's the same thing. There's something wrong. These values are different. Mm, Okay, maybe we'll come back to this, but this shouldn't be the distribution we should be having. So because these values are different, so I'm trying to. Oh. I'm using lambda. People didn't. I was supposed to use cafe. We are supposed to use the probability. So because lambda is 12, so I'm just plotting Everything 12, 12, 12. So did you guys get that? So that means you weren't paying attention. So
I was paying
here,
attention, but I know to like talk that one.
mm, okay. We're supposed to plot the number of outcomes with the probability, with their individual probability. This is the difference probability of the 25 outcomes that we see. So now we see that okay, since the mean is 12, right? So there's a high chance that 10, 11, 12, 13 people will be coming to the cafe around this time, right? So there's a high chance, so you can plan and prepare for that. Also, so let's look at normal distribution. So normal distribution, it's actually the most popular distribution that we have in statistics, and like the most important also. Now it's a continuous
Sorry, sir.
distribution. Yeah,
Yes, are we leaving that poison distribution
yeah,
stuff?
yeah, yeah, yeah.
Okay, so this thing was coincidentally I was like studying on this stuff today, sha,
All
but I
right.
didn't quite understand. So, but from the place I was studying, there was this particular out of the variables. Though I didn't really understand it, and I think probably if we discuss it in class, others might probably learn from it. So,
Okay.
from the variable, the person were given the lambda and k.
Yeah.
So then, but the person when the person wanted to identify the values or something like that, the person divined lambda, the person divide k, and the person divined I don't know if I should call it exponential or minus e as 2 points. I don't know. Can I?
Okay.
You already get what I'm saying, right?
Yeah.
Yeah. So the person wrote that minus e like approximately 2.73. So what the person did was like calculate it using the formula, not exactly. So like
Yes.
I wanted to because I did not see you mentioning that minus
Okay.
e.
So this the same is similar to the Poisson the binomial distribution. Now here I included the formula, right? So but we don't need to start coding this, already there's a package that takes care of that. So we call on the binom, right? So it does all that for us. All we have to do is to pass in these parameters, which is the number of outcomes, number of successes, the number of trials, right? Or the sample, and then the probability of occurring, and it helps you to fix the 1 minus p, the n and the k, everything, right? So k here can be x, so it's the same thing. So the formula for Poisson now is like e raised power negative lambda times lambda raised power k over k factorial. So but when we want to use this now, right, we are calling what's it called, the package now, the function. You don't need to um write out your E because it takes care of that for you. All you just have to provide, because E is actually a constant, right? Euler's number, that's 2.78
Okay,
something. So it's a constant.
2.72.
Yeah, 2.72 something. Yeah. So it's a constant, right? So you don't need to keep defining it every time. So it's already there. So all you have, what is the variable, what changes now is the lambda and the x, which you get. And lambda is the mean, the average, and then x is the number of outcomes,
Oh, yes, I
right?
get it now. Thank
All
you.
right. Okay. So now we have continuous variable continuous distribution. Sorry. Yes, continuous distribution, normal distribution. So normal distribution is also known as the Gaussian distribution. So it actually has a bell shape and it's symmetric, right? So it takes into the normal distribution, the standard normal distribution takes in, or the normal distribution takes in two parameters, which is the mean and standard deviation. And for your standard normal distribution, you have the mean to be um one, right? Yeah, the standard deviation to be zero. So, all right. So let's dive into this. So now the normal distribution is a continuous variable, right? So we are going to make use of the lean space instead of the A range now. So lean space divides. So what it does that it starts from this number, ends here, and divide it into this number of times, right? So now we're going to get between 140 and 220. We're going to get 100 equally divided numbers. Right? So exactly. So this is the start, this is the end, and this is the number of times I'm going to divide it. So if I write um maybe 2 to 5 and I put 100, it's going to divide the numbers between 2 and 500 times. So you're going to say 2.0 something, 2.3. So you're going to divide it 100 times. So that was me. So because we're having we're looking for decimal numbers now, right? For our continuous variable. So that can help us, indicate either height, like that. So we can have decimal number. And then we have the norm now, which is the function, and we're using PDF now because it's a continuous random variable. So here we pass in our x, the mu, and the sigma. So mu now is the mean, and sigma is the standard deviation. So when we do this, it's similar to what we've been doing. So we get the probability of having each of these numbers when you run it. So here, when we also plot it, we can see that it follows like a bell curve, and then the standard deviation determines this extra edge here, how deviated it is from the mean. Right. So let's look at an example. So, okay. So we have a floor bag is labeled 1 kg, but the filling machine has a standard deviation of 0 point. So we time now we're going to talk about hypothesis testing, and where sometimes maybe you have a question you want to answer, and then you can use statistics to actually answer the question and then make decision based on that. So we have a floor bag is labeled 1 kg, right? But the filling machine has a standard deviation of 0 0.2. So now, what information can we get from here? So already this is, that since this is explicitly said that it's standard deviation, so this is the mean, right? So a floor bag, that means most of this floor bags will be 1 kg, 1 kg, 1 kg. But there are times because of the standard deviation, 0.02. So there are times it could be less with 0.02, it could be more with 0.02. So when we want to do this now, so we define our mu, right? Our mu, which is the mean, to be 1, our sigma, which is the standard deviation, to be the 0.02. And then we have we want to also get the probability. So let's call it W. And then that means we're still not dealing with weights here now. And so we have the norm. That's what do I write here now, guys? Is it PMF or PDF?
PDF.
All right, PDF,
PDF.
because all right, awesome. Because it's a continuous variable, right? So we're getting decimal numbers. So when we do this, first of all, let's view this lean space so that we understand how it works. So let's
So I
so
still have a
now
question though.
all right, what's the question?
Yes, so you were talking about the link space
Yeah.
that it divides a range of number
Mm.
100. Like, can we go to the first code I wrote? Probably when you're done, that divides it 100 times. 100
Okay,
times rather.
we can do the same thing here. So lean space, and then for example, we want to, because now the range of this now should be between, since most of the distance is 1, right? So maybe some of them will fall between 0.9 and so 1.1. And then we can, let's say, divide it 10 times. So we can break it down to, like, small values. So now let's print this out so that then Joshua can ask the question. Sorry, this is okay. What's wrong? Okay, I didn't pass in anything here, but I'm coming. All right, so we see that from 0.9 to 1.1, it divided it equally into 10. 1, 2. So what's your question, Joshua?
Okay, yeah, I was about to ask the, I don't know if it will be correct. I wanted to ask what the distance or the gap between the numbers, but since you already mentioned the quality, then another thing I wanted to know was the application. I know you mentioned it earlier, but my network is really bad this night, so I can't really catch everything you're saying.
Okay, okay. So, like I said, this is actually very important because most real life data you're going to be getting would follow, like most real life this thing follow the normal distribution, just like we saw in the last class, right? So heights of adult humans. So there's a high chance that if you get up to 1,000 people and you measure their height, right? There's a high chance that it's going to follow a normal distribution. It could also be skewed, right? But then that's why the central limit theorem told us that the more you increase the sample size, the more it's going to look like the normal distribution, right? We saw that last week. So we're going to this, and this is just us trying to first of all simulate it and then find the probability of different distance. So of different values that we can get. So we can see this. So for your question of how it divides it, it does that automatically. If I put it into 11, the interval will just depend on the number you're getting, right? So now it's smaller with this number. We're gonna get 11 digits now that's divided it into. So let's say 16 now, for example. So it will just do the calculation normally. So the interval depends on how many are dividing it into. Right. So but it's gonna be equal between them. So that's what the lane space does. So in order to view this, so we have our PLT dot bar and we have the X weight and the what are we plotting against W probe. Oh, interesting. So because they are little and then let's make this 10. They'll still be very close to themselves. So let's use bar plot so that we can put in bins. But basically, this is not a good representation because that's from the sample now, our values are really close to each other, right? So the probability, okay, if let me increase the range here so that we can see it clearly. So let me put 0.2. So this is very unlikely since they said most of the bags weigh 1 and the standard deviation is very small. So that means most of them, you may not even notice the difference, right, in their weight. So, but let me put 0.5 and 100. So now there will be like, a difference and we can see the values. You know, okay, this is still actually between 0 and 1. So where we're going to see much difference is examples like this where we put the values between like 100 and this. So like there's a wide range. So yeah, uniform distribution is actually just a distribution. So let's say a number between 0 and 1. Like it's just it's lean. It's okay. This is how it is. Yeah. So if you look at how it is drawn, just like the way we say that the normal distribution is bell-shaped. The uniform distribution is like just like a rectangle, starting from this particular value 0. So if you draw a line up here now, and then it's just like a constant value, right? It's a constant function that regardless of what you have, the output will be 1. If you look at the formula, all right, the output is always 1. So regardless of what your interval is, A and B, the output will be 1. So now, so in order to still emphasize some of these things, so let me give you questions and then you tell me which distribution it is and how we'll go about it. So now, what distribution is this?
Poison distribution.
Poisson distribution. Why do you say Poisson distribution? Somebody else should answer. Why did we say Poisson distribution?
Poisson distribution because it includes time. It's time related.
It's time related. Good. So because we see this, you just have just the average, right? And then the time, right? Per week, 0.5 crashes per week. So this is of course not realistic because are you gonna get like 0.5 crashes? But it's actually like maybe in Nigeria it's possible. Almost having an accident and then you get delivered. So now we have this. So what do we do? We have to define our values and then how do we know the probability of having a 0 crash in a week? Do we just guess the value? That I think the probability should be between 0 and 1. Sorry, the probability should be between a 50 or 70. 70%. That would be 0.7. So who is helping us out? Yes, 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 we're waiting. We just have one parameter here, so it's very straightforward.
Okay, so lambda is equal to, so I'll do it in parts. I'll do the part that I remember.
All right, so we have, let's call it lambda. This is safe to call it like that. It's when we put the right, yeah.
So
So yes, it's
the
all
average is 0.5,
0.5,
and then k, I think,
Mm-hmm.
is zero, right?
Zero.
Um,
No, K is the number of outcomes that
okay, that
possible
we
outcomes. Yeah, 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 yeah. So how many like we can have zero
let's
crash
do.
rate?
I should do 15 now.
Okay, 15. So are we going to use lean space or A range?
NP dot
Mhm.
a range.
Yeah, so we're using A range because we need whole
Then
number.
yes,
So either we can have zero crash or 15. That's a wide range. But let's use it that way. And then we say, let's call it the crash probability. And then we say Poisson, right?
yes,
That's PMF. And then we have K. Oh, I'm saying, okay, you tell me, okay. There are other examples so that you guys tell me. So what's missing? I didn't get an output after running this. So of course, what do I need to add
that to
to get?
print crash probe.
All right, so we need to print
So,
that
sir, you
out.
said something about the A range. I wanted to ask a question after the class before. Well, I
All
think
right,
I've
all
lost
right.
it now.
Okay.
So you said since we are dealing with whole numbers or something that we should use A range.
Yeah.
So I wanted to, because my question before was if the A range was the same as the normal range that we use.
Yes, 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 yes. It's the same. That the normal range we use, that's for lists, right? So
Yes.
this is still like a list. Can you see this like a list of numbers? But it's for MP, it's for NumPy, it's for the NumPy package. That's why.
Okay. So is there any parameter I was supposed to pass in if we wanted decimals or something?
We want the decimal, so that's why the lean space is there. So you have lean
Okay.
space, yeah. So this just gives us the whole numbers, just the same way range works, right? Numbers
Yes.
between this and this, yeah. So one less than this, and then you can skip if you want. If you wanted to skip, you can do that. So, but this is just basically it, and that's the parameters we take. Except you cannot convert it to what's it called floating point numbers, right? So that you not get decimals here, or you divide it to another number so that you get decimals. Well, we have lean space, so that makes it work easier. So how do we visualize this?
PLC does.
TLC dot bar
All right, that's about,
K from our crash probability.
all right, awesome. So, so see that's there's very low chance of having even 4 crashes in a week, 6 to this thing. So we see zero as a very high. So the probability of having no crash at all in whatever area this data was taken from will be 0.6, which is 60%. So there's a 60% chance that there will be no crash in a week. So here there will be 30% chance. So here there will be like maybe 0.9, that's 9% chance, and then it's not like a 1% chance. So that makes it 100, right? So yes, so that was a good one. So let's try another example to see if you could identify this thing.
Then, sir, please, there's a question I want to ask.
Okay.
Initially, there was when you were writing the like first set of code, you wrote NP dot random, where you set it to, I think, 24, 22.
Yeah, 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 yeah. We did not use the random, that's np dot random dot normal dot exponential dot Poisson. So remember that was how we did it the last time, right? So
Mm,
this is just taking like a different tone, different side of it, but it's still basically the same thing. So there, when you want to simulate a distribution, right? You want to simulate a distribution, so you can do that. So
Yeah.
that's when you do that. But here in this case now we have right this specific. We want to just look for a specific value. What is the likelihood that of getting 5 clicks? What's the probability? So we can just simulate this quickly using either the particular distribution and then the either the PDF or the PMF passing our values, and then we get the probability of each of these outcomes coming, because now here we define the outcomes, right? So but for the other one now, you get to um you know set in your values and then simulate the this thing, do the experiment like numerous times, right? So that it can now follow the particular distribution you want it to follow, and then you can now answer whatever question is given to you. So
It's
maybe
kind of like,
maybe we'll do
so
something relating to that so that we can see the difference, right?
yes, then can you like scroll up to that part? It's very far.
Okay. The
Yeah, the
top.
part where we did, yeah, where we did the MP dot random,
Oh, okay, okay, okay.
because it's one of something like, yes. So now, like I said, when I was talking about block box plots, that
Mm,
the fact that we don't get to like write to variables and all of that, like normally now, look at the way we are working with the lambda. We are defining lambda, we are defining and all of that and whatnot. So,
yeah.
and now when we want to plot, we don't have to define anything. We just have to write PLC. So when I wanted to like accept it, because I just had to accept it that okay, that's the way it works. So I
Okay.
accepted it that okay, if you write all of this code inside the same line, like inside the same cell, yeah. If you write everything
Mm,
inside the same cell, then it takes it as a oh. But if you look at what we did here now, mp.random was in another cell entirely. Then what we wrote in that different cell affected the next. So I wanted to know this MP that this one also that I set now, does it affect everything we run inside this file?
this MP random, yeah. If we're going to use it, right? If we're going to use it, we would see that we keep getting the same. So let's try that answer like you say. So because already is in the memory, so you don't have to maybe
Define
um
it again.
yeah, you don't have to keep defining it again in any cell. So now let's say for example we have I want to get random integers, right? And we say np dot random. So now because we've not been actually using the random now, this is where it's going to come to play now. So let's just set this is the mean now, right? Something very simple like this. And then let's print. So we see now that if I run this again, oh, I'm supposed to keep the same distance. Come in, let me run that cell again. It changes. So that means we have to define it. Okay. I get what you're trying to say. So it has to be defined in the
Inside the
block,
cell,
the cell. Yeah. So that to work. Yeah. So we have to define it. So we're not using makings of it so that I didn't really show that way. So it's
but
only is okay.
it's for after defining it that first time,
Mm.
it seemed as if it worked for that next block of code. But so that I'll not later, I'll practice it personally. So no problem.
We've not
Then
been making use of the random. So all of these, right? There's no need for this code actually. So the only use of it now will be in a situation like this when we're using np.random. So that we set this to 25 to this thing to the value we see there. So now let's do that so we can see this thing. And then
okay,
we put 45, right? So if we keep running this now, you see it's the same value every time. So
yes.
okay, it doesn't work outside of the block.
Okay, so then so there's also something to add. This lock
Uh,
that
yeah,
is
yeah,
set
yeah.
to 10.
Mm.
We have lock and I lock in pandas.
Yeah. This is different. This one is for the normal. It just means the mean. That's the
The
that's the syntax for the mean. Yeah.
Okay, so the
That's
mean the mean
mm,
would be like the average, right?
yeah. The average. That's it.
Okay, okay.
So why for poison now is lam, which means lambda, right? So it's just the syntax they use for this. But though lock, because there isn't it in here, it's not going to be confused with how we use it to subset a data frame.
Okay, so
Yeah. So let's get back to this question. Yeah. What distribution is this? So we have an email. I mean, email campaign has 10% click-through rate. If you send it to 50 people, what's the likelihood of getting 50 clicks? Sorry, what's the likelihood of getting 5 clicks? So what's the distribution here?
Binomial distribution.
Binomial, awesome. So why do you say binomial distribution?
Because it only has two possible outcomes. Either the email is clicked or not.
Awesome, awesome, awesome. So you guys are really getting it. So it's either it is clicked or not because of that two possible outcome. So we say it's a binomial distribution. And if we want to simulate this now, we want to find out, okay, if we're not simulating, we just want to get the probability of this. So we go straight to the point and then we define our variables. And what are they in this case? Who is on the call? Some other person should help us. Emmanuel or Kazim. Emmanuel Kazim, please help us with this. Like an email campaign has 10% click-through rate. So if you send it to 50 people, what's the likelihood of getting 5 clicks? Okay, Moremi, help us. What do we write?
Our N, that's our sample space, that's 50 people.
Okay, good. No, that's your sample. Okay, yeah, that's the fine.
P, that's 0.1, 10%.
Okay, good. POB.
Then K, NP dot arrange. Since the likelihood we are trying to get is 5 clicks, you can say 0 to 15.
That's awesome. Okay. And
Then
then
click probability. Binom.pmf. We are using PMF because we are getting,
it's
because
a
it's the
discrete.
random variable.
Yeah, awesome.
That's K, comma, N dot, comma P.
Awesome. So and then
It's click probability.
It's supposed to be dot.
Yes, sorry.
I think you said that I was under put underscore there. And then we visualize it, right? So how do we
Yeah.
visualize it in Seaborn SNS? Oh, I already said that. So
SNS dot bar plots.
yeah. And
Our
then
X and our X variable.
also the K in this case.
Oh, sorry, K. That's our X, is the X variable.
Yeah, and one.
Uh, and Y variable, that is the click probability.
Okay. So
Oh, yeah, sorry. X is equals to K, then Y is equals to click probability. Okay, yes.
so we have this. So the probability of getting 5. So of course we could just print this one to see you know, the so 0, 1, 2, 3, 4, 5. So 0.18. So that's like 18% chance, that's 18% probability that they would click on that email. All right, so let's continue. So we talked about what we call sampling concepts, right? So here
So we've
it's
not discussed uniform distribution.
uniform distribution. Yeah, that's what I'm saying, that uniform distribution, the outcome is always one, regardless of what is going on. So the formula is actually a constant, is what we call like a constant function, right? Because we always, let me look for an example that is an example. Um, I don't have any example here on that. Mm. So it's basically because it always gives us one at the end of the day, right? So it's what's let me uh okay. So it's not very useful in quotes, right? Because it's a constant. So and the formula is just 1 over b minus a, right? So where b minus a is like the range on the on the x-axis. So and it's always constant. So regardless, it's just like for example, you're having a function that says that f of x is equal to 1. Hmm? So take for example such a function f of x is equal to 1. So whatever the value of x is, it will always give me 1. So if you have a, we have linear functions now, okay, we say f of x is equal to, let's say 5x, right? Now, if my x is 1, just try and picture, let me see if I can write it. So if I say f of x now is equal to 5x, right? So if I say x is 1, this will be 5 times 1. If I say x is 2, this will be 5 times 2, that will be 10. So at the end of the day, I'll get like, different values of x. So when imagine I now say f of x equals 1. So regardless of what my value of x is, at the end of the day, I'll still get 1. So, and the formula now for the, this thing is 1 divided by, a, no, sorry, b minus a. So regardless of what your interval is now, so even if this is 10 minus 3, so at the end of the day, the function is saying that it should always be 1. So regardless of what value you take in here, so it's not you just get like this flat straight line like this, always, always, always at 1, always like that. Right? Depending on the different interval you choose. If you put 50 here and 100, you're still gonna get this. Right? So that's why we don't, but I'm gonna check for an example. Maybe we'll do that, but it's not really um it's not gonna be like a very good example now for now that we're trying to learn this because we'll only just be getting this. So without even solving, you already know what your answer is, right? So that's what's the probability of whatever now. It's just be 1, right? It's just going to give us that particular value. So did you get that, Mary?
Yes, sir.
Okay. So let's continue with sampling concepts. So remember we said samples are like subsets of this, and the population is a complete set of observation of interest, right? So for example, all students in a school, all the employees in a company, or the daily sales in a transaction and all. So we have okay, so now we have the sample because of course it is most times expensive to get the entire population. So we try to use the samples that we're able to get and then run our analysis with their sample and make conclusions that affect the whole population. So the importance is that the samples can provide estimates of the population parameters like the mean and the standard deviation. And once our sample has a very close value to the mean and the standard deviation, so whatever analysis we do can be very trustworthy. So basically, the higher the sample size, the higher the statistical power. Yeah, you can trust the result at the end of the day. So for random sampling, you just pick randomly, right? Everybody has equal chance of being selected, so you pick randomly. So we have simple random sampling and stratified. So simple random sampling is the same, just maybe for example writing numbers on papers and then shuffling it and then picking. So that's how you can get your sample. Or stratified, you group them right into stratas. So maybe age 2 to 5 will be in a group, age this to this, then you now pick randomly again so that you make sure that you pick from every age group. Or for example, if you do that picking of numbers, now this simple random sampling, there's a probability that all of them will just be men, right? There's a chance that all the numbers that you're just picking are just men. So you can now group them into female and then male and then pick them randomly so that you know that you get an equal number of female and an equal number of male. And then we have the central limit theorem that means that okay, the higher the sample size, the higher the approach to look like a normal distribution, right? So now when we have this, we want to simulate this. So this is where that the random set now can come so that we can have reproducible results. So this is now following an exponential distribution, right? Where we set the mean now to be 2 and the size to be 100K. So if we do this, and then what this is basically doing is all right, so what this is basically doing is we are trying to simulate a population that follows an exponential distribution, right? And then we call that our population, and we're also trying to get a sample size of 50 from it, and then calculate the mean, and then do that 1,000 times, and then we can now do view that to see how many times the sample mean is the same as the population mean, right? Mm. So now when we do this, now we already know the mean of the population is 2. So when we pick the sample size now of 50, right? This is a population of 100K, 100,000. So we can't, sometimes it's too large to handle. So what if you can get a sample of 50 and then do the analysis we want to do, and we see that we can get a result that can be used to conclude for the whole population. So here now we're using list comprehension, right? So instead of writing the for loop, individually like that, we can to use the list comprehension where we say take this action for every value in this range, right? So when this that means basically this is 0 to 999. So we want to do this. So when we say 0 to 999, that's actually 1000. So we want to do this 1000 times. So we are going to be getting random. So we are taking random dot choice, right? So random samples from this population. Let's see what population look like. So we have, so let me run this first. So we have this, right? So basically the population is 100,000, and then it will be around this what is it called? The mean, right? So zero. So in other times we've been trying to set the outcome, right? The outcome in that's what we're doing earlier. So but in this case now the simulation is something similar to what we did in the last class, where we actually just have a random number to represent the whole population or the sample. Now, but in this case, we have the number to represent the population, and then picking a sample of 50 and seeing how close this sample mean is close to the population mean. So if I print out this my sample means now, so what do I get? So I'm going to get values within the range of these two, right? So if we want to visualize this now using histograms, then we can see that. But in this case now, the highest mean that our sample mean was most of the times close to 100 times, because we did this like around 900 and something times, right? So was would be 1 point something something something, right? So it's actually close to the sample mean, to the population mean. So maybe when we increase this, the higher the sample mean will be. So we can safely say that okay, if we select randomly 50 people from this population, it could be a good representation of the whole population. Do you get the idea of all of this things I just said now? That what we're just trying to visualize here is that, because we've said earlier that once the sample mean is close to the population mean, that means we are good to go. It's like a thumbs up, right? So that means the sample is a good representation of the population. All right. So but basically, the higher the number, the better it is. So now we talked about different sampling um techniques, so type of sampling, right? So the simple random sampling. Here now we're just going, what it just means is that we're going to just use the np.random.choice, right? So select randomly. So there's no big deal here. So we have like a list of 1 to 100. And so we can just, if you want to simulate rolling of a dice, you can use this, right? So when you set the sample, for example, to be this, to be 1 to 6 now, then you can now do random the choice, like just nothing applied to the this thing here. So you keep getting different values. So if in case you want to maybe program like a game that brings this thing, values of a dice, right? So of a die. So you can do something like that. And then in this case now we want to, from this population, we want to get the size of 10, right? And then we don't want it to be repeated. So we just want different values each time we do that. And then we print this sample, and this is what we get. So now this is how to simulate simple random sampling. So you can actually use this. For example, you give people a particular number, 0 to 100, and then you do this sampling, and then okay, these 10 people will now be the ones to go to for the survey or something like that. So basically, this is another way to randomly select your sample using np.random.choice. Very simple. So here now we want to see how to do this stratified sampling, right? So first of all, we have a data frame that has 0 to 1 as the student ID. So the 1 to 100 the student ID, and then the first 50 will be men, and the second 50, the last 50 will be female, right? F. So we group them, all right, and then we select a sample of five out of it. So what we're going to get at the end of the day, it's going to randomly select five female and then random select five male. So in this case now, we are sure that according to gender, it is balanced. We have five male, female, five male, and then we can make sure that okay, there's no bias. But in this case now, it's possible that all of this now, if we should use the same thing here because we have 0 to 50 to be male, we're just going to get only one, two, three, four, five. Okay, six, six males, four females. So it's kind of not balanced, right? So this is how stratified, sampling works, and we've talked about that. And also we could get what we call our standard error, which is the standard deviation of the sample that we get, right? The difference between the standard deviation basically is how the data deviates, how the data points, right, deviates from the mean that we get. So of the mean that we have. So your standard error now is calculated using the standard deviation divided by the square root of n. So here basically we're just trying to visualize that. So tomorrow we'll be looking at, so we don't rush things. So tomorrow we'll be looking at somebody say something.
So I was saying that when you say we don't rush things, I said as I approach this one because I have to get rid of all of this thing again. Like it's not
Oh,
familiar,
okay, but
but it's fine. It's fine.
when we make use of all right, we're gonna give you exercises so that you're gonna play around with it so that it makes whole sense,
Yeah,
right?
I think that would help.
Yeah.
But
So
let it be after we have gotten the recordings,
yes,
so we
yes, yes,
can.
you get a recording on time today.
Okay.
So yes, if there are no questions, we'll call it a day and then we'll see you tomorrow, please. On time, I think 7 p.m. Nigerian time. Yes, 7 p.m. Please.
Tomorrow.
Yeah, today was just an exception. So please, 7 p.m. Nigerian time tomorrow. We meet and if we are fast enough, we should be able to go into machine learning. We should be able to start machine learning tomorrow.
Ah,
So
so let's take a break. Oh, let me tell you something. Like let me tell you something. You see this thing like this now. It's like we're supposed to understand. Like me now, I can't lie to you. The only way I can understand this thing is I have to go and read. And you see, like just to do between tomorrow now is a lot. Today and
yeah, yeah.
tomorrow is a lot. So sir, please, we can do machine
So
learning. Like probably if we have midweek class, we can do
no.
machine.
All right,
Okay.
let's see. Let's see. I thought you would be excited to do machine
No,
learning.
I'm actually very excited because
Ah,
I want to build stuff. In fact, this random game stuff, I'm thinking like I want to even, I'll use it to
awesome. So
build a game.
those are the kind of projects you do so that you can build your portfolio. And I believe you guys have GitHub account or Cargo accounts or LinkedIn. So this is where you push all of
So
this
will you
work.
do tutorial for that GitHub stuff for us?
Okay, maybe we can put that as a side dish.
Uh,